Hello everybody, we will be talking about graphs today. Let us start from the storage of the graphs. Storages. I want to ask you, are you familiar with the graph algorithms, or you're not familiar with them? That's probably the question to start with. Do you know how to store graphs and etc.?
I'm not familiar, but
Okay, so typically there are two types of storing the graphs. The first type is adjacency matrix. So you have the number of vertices here, the number of vertices here, and 1 in this matrix will mean that the vertex u is connected to vertex v. This means that there is an edge from u to v. Oh yeah, sorry, I should have started from a little bit different way. So there are two types of graphs. There are directed graphs, directed and undirected. What does it mean? It means that in directed graphs, the edges are directed. So you can go from vertex u to vertex v by an edge, but you cannot go by this edge back. In undirected graphs, all edges are kind of doubled. So they're from u to v, and from v to u, you can go by the same edge. So for adjacency matrix, this means that for directed graph, you simply put there 1. For example, for this graph, 1, 2, 3, directed graph. So we have the matrix 1, 2, 3, 1, 2, 3. There is an edge from 1 to 2. So there is an edge from 1 to 2. And there is an edge from 2 to 3. So it's simply that. So here is the adjacency matrix. All others are filled with zeros. So for example, you can use a Boolean array. There, instead of integer array, as I have 0 and 1s, you can have a Boolean array where there is true or false, where exists this edge or not. So for directed graph, if you, for example, take the same graph but make the edges undirected, so you will have this similar graph. One, two, three. 1, 2, 3. There is an edge from 1 to 2, so it is here. But in undirected graph, you can traverse by their edge back also. So we have a connection here. And from 2 to 3, and corresponding from 3 to 2, you will have 1 here. So this is adjacency matrix for directed graph. This is adjacency matrix for undirected graph. So if you would think about undirected graph in directed graph manner, we simply have here edges one way and another. This will be exactly the adjacency matrix as it is. Is it clear how to store the graph? Okay, so also I want, so each graph has, I hope that everybody understands what graph is. Probably I should have started with that, but is there any person who doesn't know what graph is? So the graph consists of vertices and edges. Vertices are kind of circles, and edges show how they're connected, how the circles are connected there. So through all the graph theory, mostly I will make that n is equal to the size of vertices, and m is the number of edges. So what is the good thing about adjacency matrix? What is the asymptotic of their query? Does there exist an edge between u and v? What will be the complexity?
If it's an array, it should be constant.
Yeah, this is simply constant. You just go to the corresponding cell in the array and just ask whether this edge exists or not. What about how to get all the neighbors of a vertex?
Links is like from A to B.
Yeah. This means that neighbors means that A and B are connected by an edge. What will be the complexity of this question?
It's an array.
Will be linear complexity?
Yeah, it will be linear, so it will be O of n, where n is the number of vertices. So you just have to follow through all there. For directed, there are two things. For directed, there is an in degree and out degree. So what does it mean? So degree.
How many edges are?
This is how many edges.
How many? If you have one, you can.
What means in degree?
Degree. How many edges are coming into it?
Yeah, exactly. Into and out degree. Number of edges out. So for the matrix, for the graph which is undirected, you know that the row is the same as the column because nobody cares. But for the directed graph, in the row, for example, in the row, this is outgoing edges, and for row is ingoing edges. So for example, here there is one outgoing edge from 1 which is going to 2. For the row, or for the column, for 2, there is one edge that is going inside it, which is 1. For example, for 1, you can see that there is no incoming edges at all because all column is filled with 0.
Just 1 second. So in this second type of graph, we have one incoming edge because we go from 1 to 1.
Can you repeat?
You said for incoming degrees, so we have only one option, whereas 1 is coming 1.
Here is here is there is no incoming edges for 1, but one outcoming edge, which is this one.
From 1 to 2.
From 1 to 2, yeah.
And we have
and there is no incoming edge to 1. For example, if I put here 3, I would have to change this adjacency matrix, this cell, and then if you look at the column, there is one incoming edge to 1, which is 3.
okay.
Does it make sense?
Yeah. And by the way, the quality is good.
Okay, great to hear. So, for example, in directed graph, you also could have the backwards edge. So you just say here from 2 to 3 and from 3 to 2. It will be 1 here. typically there is no edges on the diagonal, because typically there is no loops. So loop is an edge that goes from one vertex to itself. But sometimes it happens, so you have like this loop. So for example, from 1 to 1 there is 1. So this is one way to store graphs in the computer. So we know that there are two functions that we want, like to traverse all the neighbors and to ask where the edge exists. And we do this in constant and in linear time corresponding. So now we will talk about adjacency lists. So what it is, for each vertex we will store a list of neighbors. So for example here vertex U, it has v1, v2, vk as neighbors. So typically it is array of vectors or array of array lists in C++ and in Java correspondingly. In Python you will have like simply their list of lists. So there is no hard things. So for example for our graph, which was like that, we have has one neighbor, which is 2. 2 has one out edge, which is 3. And for 3, okay, let me do like this. And for 3, for example, it has 1 and 2 as their out edges. So the same happens with the undirected graph. So we will have 1, 2, 3 here. We will have 1 with 2, 2 with 1 and 3 with 2. So we simply store per each vertex their list of its neighbors. In this case of directed graph, we maintain their out neighbors. In undirected graph case, we use just neighbors as the neighbors, because the neighbors is symmetrical. If there is an edge from A to B, then there is an edge from B to A. Okay, so what is the complexity of traversing through all the edges of U?
It's constant time.
No, of course. It depends on the degree of deg U. So here is its O of k. This is very important thing because we will typically use adjacency lists to know exactly their edges that are coming out of the vertex. because it works not in linear time, but in the degree, which will help us to get better complexities in general case. We will talk a little bit about later. So what will, like, we want to check whether the edge exists. Can you tell me what will be the complexity?
This should be constant because we just call the cell and we check it.
To which cell? So you are asked, tell me whether U is a neighbor with V.
So we go into U and check if it is the
Yeah, but at what time?
Yeah, it's also A.
Yeah, can we do it better if they're sorted?
All log K.
Yeah, this will be logarithm of their degree if we use binary search there. Typically nobody uses this, but like so here you can see the difference between adjacency list and adjacency matrix. Adjacency matrix kind of simpler to work with, but adjacency list can give better performance, which we will understand a little bit later. So this is how you typically store the graphs in the memory on your computer. So now we will talk about depth first search. So depth first search is an algorithm that traverses over all the vertices of the graph. You start with, so for example, you want to solve the problem. How many connected components are in the graph? What would be your algorithm? You just take one vertex and try to go over all her component, kind of we traverse all the vertices in the graph in its component. So the graph can have different number of components connected. Which means that the edges, there are no edges between the components itself. And we want to find the number of such connected components.
So it's 3 components.
Here is 3 components, yeah. In this example, so like there is 3. All vertices inside one component are connected. From different components are not. So it's pretty simple. So suppose we are given a magical tool that we can take a vertex and traverse in some manner all its connected vertices. Then we will take the first vertex and traverse all the vertices in this component. Then we go over all other vertices, and if they are already marked, this means that we already were there, then we do nothing. Or if we find a vertex that is not marked yet, then this is the new component, and we go through this component and traverse through all the vertices there. The same happens with the third component, and etc. So the algorithm will be pretty simple for V inside number of inside vertices. So typically it is from 0 to n minus 1. But like, I will try to write it a little bit more generic. If was of V, if not was of V, then I tell DFS of V, and the number of components I increment by plus plus. What will be doing my DFS here? DFS will traverse through all the vertices that are connected to V and are set as marked. So there was is true. So initially was for all the vertices are the same and are false. So how DFS will look like? Let me draw this. So for adjacency matrix, it will be the following. So DFS of V if was V then return, then was V equals true, and then we traverse over all the. Okay, so let me do not for adjacency matrix, but in general. So if we was in this vertex, then we have to do nothing, we just return. Otherwise, we set that we were in this graph, we were in this vertex, and then you traverse all the edges that are outgoing from V and call DFS of U recursively. So there are two options for adjacency matrix and adjacency list. For adjacency matrix, it will be for E1 to n minus 1 if A U for VA U, then DFS of U. For their adjacency list, it will be for U in like our graph of V, then DFS of U. So that is simply how it works. So this is how we compute the connected components, the number of connected components. The question is, what will be the complexity of this algorithm? How many times do we call DFS? You call DFS for first vertex, you call DFS for second vertex, you call DFS when you are called with DFS1, then you go through the number of edges coming out of the vertex 1. The same, if we are called with DFS2, then we go over all the edges that are coming out of 2, and etc. So for adjacency list, if we go only over the edges, then their complexity will be of n. Because we can traverse through all the edges in exactly the number of outgoing edges. So there are outgoing edges from 1, outgoing edges from 2, outgoing edges from 3, and etc. Outgoing edges from n minus 1 vertex, and this is exactly the same as the total number of edges in the graph. What will happen for adjacency matrix? What would be the complexity? the silence.
So all edges and the number of vertices.
We'll call this function more times than in adjacency list.
Yeah, so can you tell me the complexity of this solid vector goal? You know what n, you know n what it is. N is the number of vertices. So what will be the complexity? So when we come with DFS1, what will be the complexity of the DFS1?
It's linear. We go for vertex -1, and we go, for example, to the right and see if it's connected, and we go here.
Yeah, okay. So for DFS1, it will be linear. For DFS2,
it should be linear.
for DFS3, okay. So what will be the complexity though?
It should be squared.
Yeah, exactly. So the complexity will be n squared. Because on each coming to this vertex, we iterate over n neighbors. So your complexity is all of n squared. That is why I prefer to use adjacency list to the adjacency matrix, because typically O of n squared is bigger than O of n. But sometimes the number of edges can be O of n squared. Can you give me an example?
When it's all connected to all.
Yeah, exactly. So when it is all connected to all, the number of edges is approximately squared. So if your graph is sparse, which means that the number of edges is less than squared number of vertices, then you should use adjacency list. Otherwise, you can use adjacency matrix and you will be fine. Okay. So this is how our DFS depth first search looks like. So what DFS is doing really? To be more precise, it builds a tree. So there is a depth first search tree. What this means? This means that if we come by an edge and call and get a good call, then we have an edge there. So like let me rewrite a little bit here. Like I typically write like that way, but let me be a little bit more specific here. If not was of u, then DFS u. This means that we go over the vertex only if it was not marked. you can see that it builds a tree. So for example, let me take graph like this. So what's happening there? We are right now in this vertex and we go to its neighbor. This means that we take this edge into the tree. Then from this vertex we can go there, but it's already marked. Then we go further. Okay, we go, this edge comes to the tree. Then from this vertex we come to a neighbor which is not marked yet, and we simply set this edge to the tree. Then we take this vertex, we see that this one is marked, and we go to this vertex. It also goes to the DFS tree. Then from this vertex, all of the vertices are marked, then we go back, then we go back again, then we go back, then we go back. So this is our depth first search tree. Unfortunately, in my example, we got their path as a tree, but like for example, if I do with that, what would be the tree there if I remove this edge? 1, 2, 3, 4, 5. So we have 1 to 2, 2 to 5, 5 to 4, and what will be, how 3 will be connected to this tree?
So 5?
Yeah, it will be 5 because 5 goes to 4, 4 looks that 1 is marked, then and 5 is marked, then we go back, and 3, 5 will be in our edge. Yeah. Exactly. What is this DFS tree is for? It has pretty nice properties. Like consider right now undirected graph. Can you tell me? So this is only the tree. Where can be other edges? So you know that there is some other edges in the graph. Typically, where they are going. For example, is it possible to have an edge between this subtree and this subtree? Is it possible that there is, I don't know, for example, this edge?
Why not?
I think it's possible to have an edge only for the root or for left part.
Okay, not exactly. So suppose that we have such an edge, okay? Then when you traversed, so what happened there? We traversed all this graph at first, and then we go to the right. However, when we traversed through all this graph, we could have gone to the left. So the tree itself will look like that. You will never go again to the same part, which you already traversed.
Yeah, if we have this connection, so we don't want to build right.
Yeah. And since if we don't have connection, then so for each vertex, there is no edges between its subtrees. So for each vertex, there is no edges here. So where can be edges? Where can happen all the edges of the graph? I mean, the idea that there is edges to the root is close to the real answer, but not exactly.
So the edges will be for root and for the children.
Not exactly. The edges will be from the node to one of its parents. Not exactly the root, but for any ancestor.
Like from 4 to 1 in, for example, in the picture. In the left.
Yeah, so for example, if we take this, so we have 1, 2, 5, 3, 4. You have from 3 to the 1 and from 4 to the 1. However, if for example I add the edge 2, 3 here, there will be an edge from 3 to its parent, or to its ancestor. Sorry, the parent is exact ancestor. Like, the ancestor is the ones that are higher in the tree.
So it's only the probability of having this connection, but it can not exist.
It cannot, it cannot exist. Yeah, but typically all other edges, so in graph you have m edges. How many edges are in the tree?
Here we have 7 edges.
No, you have n vertices. How like these edges are not in the tree. I asked for DFS tree. So you have n vertices. How many edges there are in the tree?
N-1.
Yeah, n-1, exactly. So the number of vertices in the tree is n-1. But you have m edges in your graph. So there are m-n plus 1 edges somewhere else. And I showed you that these edges can only be to the parent, to the ancestor, sorry. This will help us to solve the following problem. Please find a cycle in the graph. So you're given a graph and you have to find at least one cycle.
so we search for possible connection to the senders and then check is it already exists. Yeah.
Not exactly. Let me write the following algorithm. So there.
Build the whole tree and then check if it exists in more trees because input is larger than -1.
Yes, you can check that there exists a cycle. The cycle exists if the number of edges is bigger than n-1. This is true. But you have to find the cycle itself. So I will explain you their simpler algorithm, like one of the simplest algorithms there. So we will color each vertex in three colors. There will be color 1, color 0, color 1, and color 2. What this will mean? Color 0 means that we haven't come to this vertex yet at all. We never called DFS of V from it. If the color will be 1, this means that we are right now in its subtree. So for example, when we go here and like all the vertices on the path where we are in our DFS tree all have colors 1. So kind of we started traversing through this subtree but haven't finished yet. So we come to the vertex V and we say that its color is 1. Then we go through all the edges, and if we see that the color of U is 1, we found the cycle. Cycle from which is from UEB. So if we consider on the graph, so we are somewhere here, so all the vertices on the path to the root are marked as 1, and you see that there is an edge that comes to the ancestor. Then this is the cycle, and you can return it. Then if color of U equals to 0, then this means that we haven't been in the vertex U yet. Then we should go there, DFS of U. And finally, when we're going out of the vertex, color V equals to 2. Please note that here all these other vertices that are not only on the path are marked as 2 already. Yeah, and of course there is another subtree where everybody is zeros yet. So you can find this cycle on the way back of the recursion. Like I find a cycle, then I can go, like I find a cycle with U, and then I get out of the recursion, for example, marking here return or something like that until we go to the vertex U. Is it clear? Or there are some questions?
But why is so much this one following that I think much when because it's because it is like in recursion, it's like I mean it's not a question. Okay, so we got to the one, and if we come across another first step is also not one cycle, but why also not the cycle? First one.
Okay, so we can prove that the vertices that are marked as 1 are only on the path to the root. All other vertices are marked as 0 and 2.
Yes.
Okay, since we just proved here, kind of proved, right, that all the all the edges from it are coming upwards to the ancestor. So if we find such an edge, this means that it comes to 1, then we found our cycle.
Okay. I do understand. So, I was for a second thinking that when we come into the page and then we see that we already visited it, don't proceed, but now we actually proceed and check if it's of our.
Yeah.
Yes, sorry, I don't know.
No worries. So, this algorithm works for undirected graph, as we talked about. Suddenly, this algorithm also works for directed graphs. Why so? That was my mistake. Shouldn't have to. So right now our graph is directed. So instead of undirected edges there that are in our DFS tree, now the DFS tree is directed. So all their edges are going downwards because we traverse over all the out edges. So the question is, again, so we have a vertex and its subtrees. Is it possible to have, let us look here, is it possible to have an edge from left to the right?
No, not possible, because if it was possible, left part will be part of the right.
Yeah, the right part will be the part of the left. Yeah, so like it will be kind of like that. If we will never go over this edge. Yeah. The next question: is it possible to have edges from right to left? This is the tricky question, to be honest. sorry, like, yeah, I think we will end with the interaction because there is somebody who is drilling outside and like I can't hear almost thing. Oh, they stop. Okay, Elizabeth, can you tell again?
Sorry, I have noticed that we will traversing the graph, but ignoring some vertices from the first place. So we are not going counterclockwise.
We're going from left to right. Like we come here first, then here, then here.
Okay, so from left to right. So that's why maybe not the same answer.
The problem is that right now we could have this edge. So we can have edges from left to the right because otherwise the right part can be visited. But from right to left there is no obligation to do that. For example, let us consider this simple graph like that. If you go to the left, you will have this in the tree, in the DFS tree, and this in the DFS tree. However, this edge is from right to left. If I do other way around, so I go at first to the right child, so I go there, and then this edge also will be in the tree, not this one, but this one. So there is no edges from left to right, but there are edges from right to left. Luckily for us, you can see that edges from right to left cannot create a cycle, because all of them are from right to the left. So the only edge that can create the cycle, again, is the one to the ancestor. That's the main thing. So the algorithm for finding the cycle remains exactly the same. Just with the thing that sometimes we can get to the edge which is colored too. In undirected graph, there were no edges to 2 at all, but in directed graph, there can be edges to the vertices with color 2 that are from right to the left. Does it make sense for you?
Yeah, it's interesting.
Okay, good. Let us go a little bit further and we will solve the following problem. I will leave it. No, I will rewrite it. I will rewrite it. You are given a directed graph. Which happens to be acyclic. So we're talking about DAG. Directed acyclic graph. So, for example, I don't know, in the morning I must wear the t-shirt, then like I have a dependencies, kind of which part of the clothes I have to wear before another part of the clothes. So this is kind of directed acyclic graph. And the question is, in which order I should wear the clothes? So so I can respect all their restrictions. For example, in this graph, we can take 2 first, then 4, then 3, then 1. This graph is easy, but if I add, for example, here 5, then I don't know, then 5, 2, 4, 3, 1 is the right order. So, more precisely, the question is the following. You are given a directed acyclic graph, and you have to identify their vertices. So we have their function ID or vertex v, that an edge comes from lower ID to higher ID. So ID v should be less than ID of u. So, and we can, like for example, in their example with clothes, we should wear the clothes from their topmost identifiers to the lowest identifiers. And we will be done perfectly. But more precisely, their formal description of this algorithm is please find their such kind of permutation, if you want this word, or kind of the identifier, such that ID of the source of the edge is less than the sink of an edge. So how to do that? It appears that our depth first search helps us here. Because, for example, what would be typical algorithm for that? We could take their edge that has no outgoing edges and take it as the first vertex with the highest identifier. So, for example, here it is 2 or 5. 5 doesn't have any outgoing edges and 2 doesn't have any outgoing edges. So we can take, for example, 2. And we remove it from the graph. Then we take again the vertex that has no outgoing edges. It will be 5. Right now 4 has outgoing edge, 3 has, 1 has. Then we remove 5. Then we can see that 4 has no outgoing edges. Then we remove 4, then 3, then 1. So this will be the order. How it correlates to their depth first search. It appears that when you come to 2, which doesn't have outgoing edges, we just return from their depth first search. So, and when you kind of remove this vertex from the graph, your depth first search tree will be without this 2, and so it will find another vertex which has no outgoing edges. So the algorithm is pretty simple. So this problem is named topological sort. We like was at v equals to true or vu from edges if not plus of u, then top sort of u. And finally, we will take like their identifier of v equals to n minus, or let it be counter minus minus, where the counter is n at the beginning. So when you get out of the top sort, kind of, when you finish your top sorting, you can set that this vertex will now be their vertex with their identifier c minus minus, where let me write it more explicitly probably. So this is c minus minus here. So this is our topological sort. Can you tell me the complexity of this algorithm?
But we are doing exactly the same as the traversal, we just marking also.
Yeah, so what is the complexity?
The same as it was for adjacent list and
Yeah, so it is of M for adjacency list. You're right, Jose. It's not a tricky question. I will mention where I have a tricky question.
I think it's tricky for us.
Okay, so we got topological sort there. Can you tell me, like, that's the question to think a little bit, which will kind of move us to the next discussion. Can you tell me why in the directed acyclic graph there is always a vertex which has no outgoing edges?
In order to be a secret. Okay, I was thinking now.
Yeah, can you prove it a little bit more formal? So suppose that, so we are proving by the contradiction, right? So suppose that each vertex has an out degree at least one.
So we have n vertices and n minus 1.
This thing works only with their undirected graphs. For directed graphs, I can for directed acyclic graph, we can have squared number of edges, and we will be fine.
Maybe we can take the minimum of fourth and make sure it's a secret, or while it also have known degrees that have 0.
No. Okay.
And so if it will be true, and it's contradiction.
Can you repeat again then?
Okay, so we're taking a small graph. I don't know, is a line graph or is triangle graph?
Triangular or linear? What do you mean by that?
I mean, we can build a small graph, so it's everything. Like, okay, we can almost just do it, but. So, for example, if a line, like from just two vertices is already graph, from U to V, and if we make sure that there is no edges that have 0 out degrees, it's not possible. So if it's going from U to V and V, we lose like 2 edges.
Yeah, for the small graph, yes, this is the cycle, yeah. But what happens with the larger graphs? So yeah, so like if I don't know, for three vertices, if there is no edge, like there is no vertices without out degree, you will have this cycle of 3. Yeah. But what happens in the general case, where you have higher graphs?
I think it was, if it's not working already for me, so it will not work.
Yeah, but this is not the proof, right?
Okay, maybe so. So, I mean, you're saying that it's the side.
I mean, this can give you only the intuition that this is true. I agree with this is true. But can you probably give me a kind of formal proof if there is a vertex with like all the vertices have outgoing edges, then we will have a cycle.
Also, it might be that we will have more edges connected in the tree than n-1.
This is exactly what Konstantin told, but for example, there is this huge graph that has a lot of edges there.
Sorry, I was like trying to formulate mine, so I
We can we can use the not edges, but the path from one edge to the other edge. And in case of icyclic graph, there will
Okay, so it seems.
So we collapsed edges into one.
Okay. Yeah, it seems it's, if you haven't done this before, it seems to be pretty hard to understand what I'm asking for. So let us prove this more formally, and you will see how it can be proved. Let's do like that. So suppose that there is no such vertex, that all the vertices has an outgoing edge. Let's follow this outgoing edge. So we will take a random vertex and follow its outgoing edge. Then we take this vertex, it has outgoing edge. So let's follow it. Then we will take another vertex. It also has an outgoing edge. Then we look on that vertex, where the outgoing edge can be. It either can be to a new vertex, or it can be to some vertexes that we already visited. If it is going to already visited vertex, then we have a cycle here. Thus, it should go to non-visited vertex. So we continue to a non-visited vertex. However, at some point we get out of vertices. We have their finite amount. So we have only n vertices there. So when we come to the nth vertex, it has an outgoing edge. So it has to be somewhere to the edge or to the vertex that we already visited. Then we will have a cycle.
Yeah, it's clear.
Yeah, so it's quite simple, but if you haven't done this, so this is kind of give us the intuition. Like the next topic that I wanted to talk about is Eulerian cycle, but it seems we don't have enough time for today to talk about that. Let us talk then about a little bit different problem. We have exactly 10 minutes, I think. Yeah, we have 10 minutes and we will talk a little bit about another problem. Suppose you are given a tree, a rooted tree. This means that there is a special vertex that is the root of the tree. And you have a pre-computation, like computation in open time, and you should answer the query, which provides two vertices. Whether U is ancestor of V. And this query should be answered in constant time. So probably to start with, it is not very obvious how to solve this problem. What to pre-compute, what and how we can get their answer in constant time. That seems to be kind of impossible. But their idea is pretty simple. Let us have two additional arrays that will tell us their time that we go to the vertex and when they get out of the vertex in their depth first search. So here will be DFS of V, time in equals time plus plus, and T out equals time plus plus. So we have the time that we go in and we have the time that go out when we go out of the subtree. So can you tell me then how to use the time in and time out to check whether U is ancestor of V?
It's just literally time.
Sorry?
Just literally a time of running the algorithm, yes?
Okay, yeah, you can have a time, a little bit of time. Yeah, so like I tell you, we calculate the special two arrays, the special array T in, that means that the time where we go to the recursively to V, and T out, the time when we go out of the tree, subtree.
So maybe time of ancestor will be earlier than the child.
That's a good point, yes. The time of ancestor is less than the time of vertex. Okay, but unfortunately it is not enough, because for example, when you go to the left subtree and then to the right subtree, your time on the left, the time of the vertices on the left, T in, will be less than the time in for the vertices in the second subtree. So you have to use T out also. So, for example, like let us consider T in. So we come here 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, 11. This is time in. You can see that the time in of this vertex is less than the time in of this vertex. However, this vertex is not an ancestor of this one.
Also, it should be, okay, so it should be, time of ancestor should be less than the time of the child, and it also should be less than the time out of ancestor. No, not bigger, I mean.
Yeah, that is good enough.
So it should be in subtree.
Yeah, so if time that you come to the vertex is less than, is bigger than the time that we come to the ancestor, and they're out time of the ancestor, then we are in its subtree. Yeah, so that's it. I think this is it for today. Do you have any questions?
I have a question about trees in general.
Okay,
about
yes.
the homework. I want to find about Mars tree, but I found I should rewrite it. Okay, I'm running out of time on test 26. Is it actually a lot of tests after this?
Let me look on that. I can look. I don't know right now exactly.
I mean, if I don't proceed with the exercise because I'm moving to big stuff after trees, can I just do everything else?
Yeah, sure. You can then return.
And then I will try to rewrite it in something else.
Yes, of course. It's your choice in which order you solve the problems.
Yes, I'm so sorry.
No worries. Where it is?
Okay, I wrote 3 and Python is 26.
It's a homework for please. Okay, let me look at it. There are 35 tests.
Okay, so yes, it's better to rewrite it. Maybe if it's possible.
Okay, if you wrote in Python, I think it will not work here. So this is the problem that should be solved. Or you can always solve it using their inner libraries. So
like really, we should can just call for a tree.
yeah, you can use like libraries that can solve this problem. Luckily in Java you can do this using special functions on tree set, for example.
Okay, good enough. Thank you.
Okay, so are there any other questions? Everybody else already left, so who was there? Okay, so thank you for coming then. See you next week.
Thank you.
Thank you, bye.
Bye.